ahead and start talking through the notes. It's kind of like yesterday. The first part of your notes is those theorems that you guys just copied down. This is kind of similar to what we talked about yesterday. So yesterday we were talking about parallel lines. Yesterday we were proving parallel lines. Today we're going to talk about parallel and perpendicular lines. So we're talking about 3 lines today. So Theorem 3.8 talks about, okay, if you have 3 lines and they're all parallel, and then 3.9 and 3.10 are really similar, but they say different things, and those are talking about perpendicular lines. So let's start with Theorem 3.8. Okay, so Theorem 3.8. So Theorem 3.8 says we have 2 lines that are parallel to the same line. Okay, so like in this picture, it says, okay, remember the symbol for parallel is if you have this one set of arrows. So on A and B, they both have one arrow, which means A is parallel to B. And then if you notice that B and C have 2 sets of arrows, so what that means that B is parallel to C. Okay, so notice A and C are both parallel to the same line. A is parallel to B, and B is parallel to C. If 2 lines are parallel to the same line, then they got to be parallel to each other. So A is going to be parallel to C, which is easy to see in the picture. Kind of gets a little wordy whenever you just look at the words, but if you look at the picture, it makes sense. These 2 are parallel, and these 2 are parallel. Those other 2 have to be parallel. Okay? Now, when we start talking about perpendicular lines, like I was saying, these 2 I think sound really similar. In some ways, they kind of approach them from opposite ends. So, Theorem 3.9 says, and we're going to actually prove this one down below here, but Theorem 3.9 says in a plane, if we have 2 lines that are perpendicular to the same line, okay, so we have these 2 lines, they are both perpendicular to T. Now, we know we have the symbol for parallel, those 2 vertical lines. We're also going to introduce today a new symbol for perpendicular. So it looks like this. If, okay, we have these 2 lines that are both perpendicular to T. So if I wanted to say M is perpendicular to T, I would say M, and then the symbol for perpendicular looks like an upside down capital T. It's just perpendicular lines. So I could say if M is perpendicular to T, and N is perpendicular to T. So both of these lines are perpendicular to the same line, okay? If 2 lines are perpendicular to the same line, then these 2 lines, then M has to be parallel to N. Which, once again, I think whenever you look at it in words, it may not make a lot of sense. It may be kind of hard to see. But if you look at the picture, yeah, that totally makes sense, right? If these 2 lines are perpendicular to the same line, they're going to be parallel to each other. And we're going to prove that one down below. Okay? And Theorem 3.10, like I said, seems similar, but it's, like I said, kind of approaching it from the opposite end. So this is talking about a perpendicular transversal theorem. So this time it says, okay, if a line is perpendicular to one of 2 parallel lines. So this is starting off by saying, okay, I've got these 2 parallel lines. So L is parallel to N. Okay, so the other one was kind of proving that they're parallel. This is starting saying, okay, I have these lines that are parallel. Okay, and N is perpendicular to L. So these 2 lines are parallel. This line is perpendicular to that one. Well, the thing is, if these are parallel, if it's perpendicular to one of them, it would have to be N would have to be perpendicular to M as well. If it's perpendicular to one, it would have to be perpendicular to the other. Okay? Now, down here, we're going to prove Theorem 3.9. Prove Theorem 3.9. And once again, just kind of as a reminder, anytime we're proving theorems, I can use Theorem 3.8, 3.7, 3.6, anything that we've talked about before, anything we talked about yesterday, I can use that, but I cannot use Theorem 3.9 or 3.10 to prove this. Okay, they go in order. So, to prove Theorem 3.9, saying in a plane, okay, R is perpendicular to T, so notice that it's marked with the little square to show that it's perpendicular, and S is perpendicular perpendicular to T. I'm trying to prove that S and T are parallel, okay? So we're going to do a two-column proof for this one. So remember, with our two-column proofs, we're going to have our statements and then a second column for our reasons. And even if we have no idea where we're going to start, my first statement's going to be the given. So we know that R is perpendicular to T and S is perpendicular to T because it is given to me. Awesome. Okay, now, we haven't done a whole lot with perpendicular lines yet. What does perpendicular mean? Where they cross, if R is perpendicular to T, that point where R and T cross is a right angle. So this point right here, angle 1, which it's labeled, is a right angle. So angle 1 and actually angle 2 are right angles. Angle 1 and angle 2 are right angles. And I know that. I mean, it's the definition of perpendicular lines. That's exactly what perpendicular means. Okay, now take that, kind of expand on that. If angle 1 and angle 2 are both right angles, what could I say about angle 1 and angle 2? They are corresponding. We're actually going to say that in the next step. If they're both right angles? They equal 90 degrees. If they both equal 90 degrees, they're congruent. That's what I'm trying to get at you. Okay, they're congruent. Angle 1 is congruent to angle 2. Can I know angle 1 is congruent to angle 2? Because they have the same measure. And we know that angles with the same measure are congruent. Angles with the same measure are congruent. The definition of congruent angles, right? Okay, now, I'm going to build on what Elijah said. Elijah pointed out, well, 1 and 2 are corresponding angles. You guys see that? Right? Angle 1 and 2 are corresponding angles. Angle 1 and angle 2 are corresponding. Now, the reason for this, and this is one that when I copied down this proof from your book, and your book didn't include this step, but I think it's important to include this step. We'll see why in the next step. The reason for this, it's in the diagram, right? Okay, so I think we can just say, okay, diagram, picture, given, okay, it's given to you, right? It's just in the picture, okay? Now, why is it helpful or why is it useful if they're corresponding? Why do I even need to know that? What do you think? Exactly. Remember, yesterday we talked about the converse of the corresponding angles theorem. I know they're corresponding because I can see it. Angles 1 and 2 are corresponding. I know they're congruent because they both measure 90 degrees. And if I have congruent corresponding angles, the lines have to be parallel. That was the theorem that we talked about yesterday. So, since they are congruent and since they are corresponding, I can conclude that R is parallel to S because of the converse of the corresponding angle theorem. And there's our first proof for the day. We have 3 of them today. 1 down, 2 to go. Yay. Questions? All right, let's get this glued into, it should be page 39. Page 39. This is section 3-4, parallel and perpendicular lines. 2 proofs. All right, here we go. Okay. First one, it was kind of hard for me to come up with examples, and you'll see whenever you get to your homework that the examples are kind of limited, but the one in your homework is going to be kind of similar to this. So we're going to draw a fun little diagram here. So you're going to draw like a bow tie, kind of. that? A bow tie? Yeah. A sideways hourglass, yeah. And then connect the tops. There we go. I thought that was the easiest way to describe this. Okay, and we're going to label A, B, C, and D. Okay, before I give you, because I'm going to give you some angle measures too, but before I give you the angle measures, what they're asking here is saying, what's the relationship between segments A, B, and CD? So A, B, and CD. So I'm going to give you some more information, but I'm just wanting to know what could you conclude about them. So here's the other information we're going to have. We're going to say that this angle is 68. That one is going to be 22. This is going to be 35, and this is going to be 55. Okay, now, we could probably make like an educated guess, right? What would you guess we could conclude about A, B, and CD? I'm going to guess they're probably parallel, which you're probably right, but we have to like back this up with, math and stuff. So let's go ahead and say that, okay? Segment AB is parallel to CD. Okay, great. I've got to be able to back this up with reasoning, a theorem, a postulate, okay? If these are parallel, okay, there might be one of the theorems that we talked about today that possibly talks about parallel lines. What do you think? That would be a way to think about it. We could do that. If you add these together, what would you get here? 90. And if you add these together, you get 90. Okay, so I could say, all right, so I have same side interior angles that add to give me 180, which is the converse. Okay, you could say the converse of the same side interior angle postulate. That'd be one way to prove that. Okay, that they're parallel. I could also use one of mine today. Okay, now, here's where it can get a little tricky because I mentioned this, that these two seem really similar. Okay, so you have to think about what information I'm given. In this example, I know that these two angles are 90, right? I do a little bit of math, but I know these two angles are 90. I know that since they're 90, both of those lines are perpendicular, right? And if I have two lines that are perpendicular to the same line, we can conclude that they're parallel. So you could also use Theorem 3.9. And Theorem 3.9 says if two lines are perpendicular to the same line, the lines are parallel. Either one would work. You could definitely use either one of those. Okay, questions on number 1? Okay, now we're going to go through two proofs. We're going to do the first proof as a 2-column proof, and then we'll do the second one as a paragraph proof. I definitely prefer the 2-column proofs, but your book does use paragraph proofs a lot. I want to make sure you guys are exposed to all types of proofs. You have experience with both of them. So it's actually going to be super similar problems for both of these. Number 2, okay, we're going to be given, okay, C is perpendicular to B, B is perpendicular to D, and D is perpendicular to A. My job is to prove that C is parallel to D. A lot of information there. C is perpendicular to B, B is perpendicular to D, D is perpendicular to A. I want to prove that C is parallel to D. Okay, now we've got a diagram. Okay, So we're going to do two vertical lines that are going to be A and B. Two vertical lines, A and B. Okay, we'll draw a horizontal line up here at the top that we'll call C, and then one down here that we will call D. When you have a two-column proof, it's usually helpful if you can talk about the angles either by naming them or by giving them numbers. So let's also number our angles here. Let's do angle 1, 2, and 3. And then lastly, before we start our proof, a lot of times they're going to label the diagram for you with information that you're given, but sometimes they don't. So if you remember, whenever we very, very first started talking about proofs, we talked about how it's helpful to label your diagram with any information. So if I know that C is perpendicular to B, I know that that's a right angle. So we can go ahead and label that. Sometimes we'll do it for you, but sometimes not. I know that B is perpendicular to D, and D is perpendicular to A. So I can go ahead and mark those on there as well. All right, so let's set up our two-column proof. We've got our statements and our reasons. Now, you are allowed to use any of the theorems we've talked about so far. Okay? So any of the ones we've talked about today, any of the ones we talked about yesterday, earlier this year, okay? The first statement, we kind of already know what it's going to be, right? It's going to be the given, but here's the thing. You may not need all of this, okay? And it's not necessarily wrong if you write it all, but if it's not necessary, it'd probably be better to not write it. If I'm trying to prove that C is parallel to D, I don't really have anything to do with A. I don't think anyway. So for my given, I'm going to say, okay, C is parallel, or C is perpendicular to B. I think I'm going to need that. And B is perpendicular to D. I'm probably going to need that too because I'm trying to prove that these are parallel. I don't need that last one. So once again, it's not wrong if you write it, but if you don't need it, it'd be better not to write it. Okay? And that is going to be the given. Okay, now, kind of like we did in our first proof on the left side of the notes, since they're perpendicular, what do I know? They form right angles. Angle 2 and angle 3 are right angles. And I know that they're right angles, because that's just the definition of perpendicular lines. Now there's a couple ways that you could do this one. We could prove this basically the exact same way we proved the last one, right? But if I'm allowed to use the theorems from today, think about it. I have two lines that cross at 90-degree angles with the same line. Isn't that enough to prove that they're parallel? Yeah. So I could go ahead and say, okay, well, I could say, okay, C is parallel to D. C is parallel to D. Which of my theorems today says that if I have two lines that are perpendicular to the same line, then the lines have to be parallel? Humberto? Well, 3A was all the parallel lines. So it'd be this one, right? If I have two lines that both form 90-degree angles, okay, then those two lines would be parallel. Now remember, you can't say Theorem 3.9 because Theorem 3.9 in our book may be different than Theorem 3.9 in the books. You kind of have to, since this one doesn't have a special name, you just kind of have to explain it, okay? I know that they're parallel because, let me give myself a little bit more room here. If two lines are perpendicular to the same line, the lines are parallel. There we go. Two lines are perpendicular to the same line and the lines are parallel. Okay, so that would be our two-column proof. Not too bad. Yeah? Yes? No? Maybe so? Okay. Alright, we're going to do pretty much the same thing. It's going to have the same given. It's going to have a different proof, but it's going to be the same picture. This time, it's the same information, but it's going to be given to you a little different. So this is going to say, in a plane, C is perpendicular to B, B is perpendicular to D, and D is perpendicular to A. So same given, just says in a sentence, okay? C is perpendicular to B, B is perpendicular to D, D is perpendicular to A. We want to prove that C is perpendicular to A. C is perpendicular to A. We're going to have the exact same picture. So A and B are going to be those vertical lines. C is going to be a horizontal line up top, and then D will be this horizontal line down here. And we can go ahead and mark our angles since it's given to me. Again, that these are all perpendicular. We can mark them all as right angles. For a paragraph proof, it's not usually as necessary to have the angles labeled. You could if you wanted to, but I don't think we'll need it for this one. Okay? All right, so we're going to start this one a little bit different. So with the paragraph proof, you usually start with the given, but maybe not like the whole thing. So if we kind of think about a game plan here, okay? I know that these are all perpendicular, okay? I'm trying to prove that C is perpendicular to A, okay? So we're going to have kind of a multi-step process here. Okay, we're going to have to kind of tie some things together. What do you think we're going to do?
C is perpendicular to B is perpendicular to B. So then when C and B is perpendicular to C.
Right, so we're kind of tying both of the new perpendicular theorems together, okay? So the first one, all right, we know that C and D are parallel. We just proved that, right? Okay, because they're perpendicular to the same lines. But even though it's a new proof, we're going to have to kind of say that again, okay? So we can prove that C and D are parallel, okay? Here's the thing. If these are parallel, if D is perpendicular to A, that's that other theorem that we talked about. If you have parallel lines, if one is perpendicular, the other one has to be perpendicular. Okay, so that's kind of our game plan here. Does that make sense? Okay, so let's put that in works, okay? So we're going to start by saying, okay, since B is perpendicular to C by the given, that's given to me, B is perpendicular to C by the given, and B is perpendicular to D by the given. C is parallel to D. And you have to explain how we know that. Because two lines perpendicular to the same line are parallel. So we have B is perpendicular to C and B is perpendicular to D, because that's given to me. I know that the lines are parallel. That's what we proved in the last one, okay? Because two lines perpendicular to the same line are parallel, okay? Now what we can do, now that second part, okay? Remember we said, since these are parallel, okay, if this is perpendicular to A, then that has to be perpendicular to A, okay? So, since C is parallel to D, and D is perpendicular to A, C has to be perpendicular to A. And that was Theorem 310. Now remember, you can't say Theorem 310 because our Theorem 310 may be different than somebody else's Theorem 310. So what Theorem 310 says, if one of two parallel lines, if one of two parallel lines is perpendicular to another line, the the other parallel line is also perpendicular. There we go. There's our paragraph proof.